hopefully many of you have already installed Corvus. I know there can be some issues with both Windows and Mac in the case that you already have a Python version that you are using and you like. Just to note again, if you tried to install it and you don't really use Python, but you have it on your Mac, I think Mac always comes with Python. If you said, you can always just, if you don't really use Python, I would really suggest that you just go ahead and let the installer install Anaconda Python, because I'm pretty sure that will work to install Corvus. If you use Python and you don't want to, add an extra Python there because it might mess up your environment, then you can always email me if you have problems. Also, you can reply to the registration email if you registered for FEFF10. You can just reply to that with questions. That'll come to me as well. Okay, so just to give an idea of, DOS already kind of went through this, but of what Corvus is for, it's basically a workflow framework that allows you to run allows us to write various workflows and you to run various workflows that combine different calculations of using FEFF or calculations using FEFF and other codes, or just other codes to get advanced calculations of spectroscopy. So for example, using DFT for just one of the simplest cases, using DFT to optimize a molecule or structure, and then calculating the spectrum from that. So again, let me just run through installation really quickly in case we had people who were not here for the first part. There are some requirements for Corvus itself. You don't need Java, but for the general installer, which installs both Corvus and FEFF10 and JFEF, you'll need a Java. And it's different for Mac and Windows. And then you'll also need Python. Again, I strongly suggest that you use Anaconda for these if you don't know Python well or use it a lot already. But we can work that out over email in the future if you have problems. Okay, so if you need to download it, you can go to the website here, which is in the chat a little bit earlier if you scroll up. It's Times Software, github.com/times-software/Corvus/releases/latest. And there are instructions there with all of the details of all this stuff if you need it. Once you start downloading and installing that, it's going to install FEFF. And when it starts doing that, it's going to ask you for a password and tell you to go register if you haven't already. You can always just enter the password if you've already registered. And if you haven't, then you can go to the registration page. Windows and Mac both kind of try to keep you from installing things from the internet, so you might have to get around that by looking carefully. On the Mac, when you download the installer, you want to open a terminal, change directories to downloads, and then type sh space and then the installer. Okay. And then to run on Windows, what we're going to do is you can look in your start menu and there should be a Corvus folder with Corvus inside it, and you can start it that way. There's also an icon on your desktop. In Mac OS, you open a terminal and type conda activate Corvus. This is if you installed with conda with the installer. Then that's what you're going to do. And I'll show you how it looks here. So there's Corvus, and I'm going to hit that. You probably won't get this red stuff, or you might, I don't know. But you can see here it says Corvus This is a PowerShell window, so it has all the PowerShell commands that you'd use. Some of them are similar to Linux, like ls will list the directory you're in, or cd will change directories. But you should be able to type run-corvus, and if you type that alone, then it will say provide target properties or workflow. Now, let's go ahead and just go run a simple calculation. It also installs, or should install, in your home directory. So this starts in your home directory. So you should be able to change directories into something called Corvus examples. And you can type ls again, and it will show you all the examples it has. Most of these have to do with other codes, not just FEFF. So they won't work, right? But we'll do some examples that correspond to either just FEFF or FEFF and some other Python code, which all those work. So let's go into FEFF Zanes and GECL4, our favorite tiny molecule that runs really fast. So we can look, type ls and see what's in here. And you could type notepad GECL4.in just to see what it looks like. It kind of doesn't look so different from a FEFF input file for this tiny molecule. There's less stuff though. We're basically telling it that what we want to calculate, this is our target property list, target list, is we want to calculate Zanes. We tell it the edge and the absorbing atom, which is the index in this list. So that's the germanium atom. And then the list is basically an XYZ style format, just a cluster of atoms, right? So this you could pretty much just copy out of an XYZ file if you wanted to do that. Okay, so then you can do run-corvus -i GECL4.in, and that should run it. And of course, this isn't really much of a workflow because all it's doing is running FEFF, and you could do that with JFEF if you wanted to. But you need the input file, of course. So now I can type ls again, and you should see, originally when you go to this directory, you will only have GECL4.in. And now you should have this corvus.zanes.out, which I can type notepad again, corvus.zanes.out. And that shows it's just two columns. The first one is energy, photon energy, and the second one is absorption. And then also you should see that there is this Corvus1_FEFF directory. And that's where, I don't know if you noticed, you probably didn't because it's up at the top here, but if you scroll back up to the beginning of the calculation, it shows you the workflow that it's going to use and the different steps. So it's got step 1 is calculate Zanes using FEFF. And so the Corvus1 corresponds to the first, it's the directory that holds the first step of the workflow. So you could list what's in that directory, and it shows you all the stuff that's in there, and this is all the output of FEFF. So we could, for example, open again notepad Corvus1_FEFF and just look at what FEFF input file it produced. Okay, so this looks like a FEFF input file. There's some default stuff that we have in there. I'm not going to really go into that, but if you wanted to compare that, or if you wanted to open that input file with JFEF, then you can do that. And then finally, you also have xmu.dat, which holds all of the output, all of the spectroscopy output of this Zanes calculation, which isn't all in corvus.zanes.out, it has other columns in this xmu.def. So if you need to find that, that's there. Okay, so this was a very simple Corvus calculation. But you would like to be able to understand what the Corvus input-output structure is. Generally, the output is in corvus.property.out, but that doesn't always have all the output that the executable produced, so you might want to look into those directories that are created. So the input, we really try to make it so that you really only need a very minimal amount of information. So the main things that you need are to ask Corvus to calculate a property. And then you need to give Corvus whatever the required input is for that property. And you can look at the Corvus documentation if you want to see all of this together in one document. Right now, it's just a text document. We will be updating it. So let's just go to that the Corvus download page, because it has the documentation in there. There it is, Corvus manual.txt, and we'll open it with Notepad, and it has lots of information in here. There's stuff on the general structure of Corvus, and how to obtain it, and how to install it, and how to run it. But one of the main things down here is input structure, where it will tell you kind of the general format of the input, which is always a keyword, and then curly braces, and some value or set of values, right? So it can be just a single value, it can be a single array, or it can be a bunch of lines, right? So that could be a double array, for example. It could be a bunch of values on one line and then a bunch of values on the next line. So that could be something like an XYZ style format, like you saw with GCL4, or these could all be strings, for example. And they each have unique formats in terms of the values. They have, for some keywords, those have to be strings, and for some keywords, those have to be integers, and for some, they have to be floats, for example. And you can read through all of that. It talks about all of that down here. I'm not going to get into it too much. But once you read through that, then you'll want to know what are the target properties that we actually have available to you. And how do I specify what those target properties, what target properties I actually want Corvus to calculate. So again, like we saw in GCL4, you give it this target list, and then you can give it a list of properties. They're just strings separated by spaces. That's how the lists are specified. They're separated by spaces. So for example, if I wanted to optimize the structure and then calculate the Zanes, that's how it would work. Of course, for optimized structure, you need some DFT code, not just FEFF. And then there's a whole list down here of all the properties that you can calculate with FEFF, or not with FEFF, but with Corvus. And then the codes that are required, at least, this doesn't have all the codes that are required for every property. Some of these only require this code, but at least this code is required for any of these properties, right? So some of these say FEFF, and that's the only code that's required for them, right? But other things maybe, so for example here, MB Zanes, that's many body Zanes, that requires this MBConv code, which we will make available. That should work on Windows, but it also requires Siesta and FEFF. So anyway, hopefully we can, make this a little bit more clear on exactly what's required. But in terms of the codes fairly soon. But for simple workflows, this works to just look at what's required here. But also, if you know the properties, you know you want, say, Zanes or spectral function. Let's look at spectral function. Actually, we'll do Zanes first. You can also use the command line help. So you can do run Corvus, and for some reason this takes a bit of time, but -H and Zanes. So it can be either -H or -- help, and then you give it a property or an option. And if you give it a property here, like Zanes, then it again shows the workflow, which has what it's going to calculate. It doesn't actually calculate it, of course. And then it'll tell you what the output is. And then it tells you required input, user input, which is a cluster and an absorbing atom. And then down below that, it's going to give you help for cluster and absorbing atom. And so here it tells you that the cluster is given by atomic symbol X, Y, and Z coordinates. And then absorbing atom is the index of the absorbing atom for core spectroscopies. And it counts from 1 for the first atom in the associated cluster, which is up here. So again, this might make more sense now when we look at GeCl4.in. So now we have these curly braces, and we've got our cluster here, and we've got the absorbing atom corresponding to that cluster. And you can see there's FEFF.edge here. Okay, so that's one way you can use the help. The other way you can use it is to just give it an option rather than a property. So you could say, for example, absorbing atom. And that should give you the help for absorbing atom. You can also give it anything that you think might start with. You can give it something to search for, at least in the start of any of the options. So if I type FEFF here, it will give me all of the options that start with FEFF. So what we tend to do in here is we have general properties that don't start with the name of a code, and then specific properties or options that come with the beginning of the code. So FEFF, all the options that are specific to the FEFF code, like FEFF.scf or FEFF.fms, they start with FEFF. So that's a good way to kind of get an idea of what you can do in terms of options for FEFF. And then finally, you can type run Corvus -H all, and that will give you all of the options that are available. It's very long though, so you may not be all that useful at the moment. Actually, there's one more thing you can do. If you have an input file, then you can give it the input file with -I GeCl4, and then add the -H and just put whatever you want at the end. Just something that isn't blank space. And that will give you the help for whatever property was required or requested in the input file. So if the input file requested more than one property, then we'll give you the help for that. Okay, so let's go back to our PowerPoint. At least you have some idea of how to get some help here. So let's look at a more useful example, which is the fitting example, which I think you already ran maybe earlier with DOS. But we'll do the fast fitting, which just fits the calculated germanium tetrachloride spectrum to experimental data. And it does it by varying just the broadening the Fermi level, an absolute scaling, so just, you know, the normalization, and an absolute energy shift. So to do that, we can go up to directories so that we're in Corvus examples again, and then cd fit gecl4 underscore fast, and oops, type ls, and you should see just gecl4.in and exp.dat. So that's this experimental data is needed in there. And you can, again, look at what's in here. Oops, I just typed notepad without. Okay. We can look at what's in here, and it asks for a fit. So fit is kind of a special keyword or special property that you're asking for because it has its own sub-property. So you want to fit experimental zanes. So you have fit.target as well. So this means that you can also put XES here, for example, and in the future we'll have other properties that will be possible to fit as well. And then you define the experimental data, or tell it the experimental data, and you define some parameters. And like I said, here we have an amplitude, a shift in the Fermi level, an overall broadening, and just an overall shift of the spectrum. And some of these things you might need to use, others you might not. I have a bunch of other stuff in here. I think you should be okay if you get rid of most of this other stuff. But we'll go ahead and run Corvus on this. And that should run FEFF once, basically. And then it only runs, for all the rest of the times that it runs FEFF, it's only varying things that are very small calculations. So it does things really quickly. Now, if you were to vary, instead of, for the fit, if you're to vary something else that changes the structure, then you have to recalculate the potentials and the spectrum completely from start every time, and that won't be so quick. So something I forgot to mention before is plotting. There isn't really a way to plot within Corvus, so you want to have either your own plotting software that you like to use, that you can use to plot the output, or you can, if you don't have one, this is not ideal, but you can use JFEF to plot any of the things that are on here. So I'm going to go ahead and just hit plot. It's going to give me an error. Oh, maybe not. It didn't give me an error because it plots copper, but that's okay. I'm going to get rid of this one by clicking delete, and then I'm going to do file, open, and I need to go to the directory where I just ran Corvus and look at this thing. So it's in Josh, Corvus, examples, fit, gecl4 fast. And you can see corvus.fit.out is right here. That's the output. So we can open that. Oh, maybe this didn't work the way I wanted it to. Hang on, let's open this one. I'm going to open one close to that. Let's go into the FEFF directory. We've got gecl4 fast, Corvus 1 fit. Inside that, there's a Corvus 1 FEFF, and we can open xmu.dat, hopefully. It's giving me problems. Okay. So let's just close this, and I'm going to open that input file instead. Okay. Go to Josh again, Corvus examples, fit, GCL4 fast, Corvus 1, FEFF.inp. Okay, now I should be able to plot the xmu.dat that is in that directory. That seems to work, although the color is not so good. Okay, you can see that. This is just the last calculation that was done. But if I go back and open oops, GECL4 fast and corvus.fit.out, now that gives me a file, and I can get rid of this one because that doesn't include the shift. And now I can also open it again, corvus.fit.out. And I'm going to plot column 3 instead of column 2. Column 3 is the experimental data. So that's what my fit looks like. And, you know, this is not perfect, but I didn't really fit very many things. There are also some issues with FEFF's spherical muffin tin approximation, for example. On these small molecules, there can be problems, and that's what causes this hump to be missing from the calculation. But still, I think you could fit the bond lengths, for example, if you wanted to, and get a pretty decent, you know, a pretty decent fit to the bond lengths given this sort of x-axis oscillation out here. And you can try that actually if you want to in the, let's see, where's the, there it is. Okay. In the other GECL4_full directory. But then also you can look at other things that are in this directory that we ran here. And you see there's fitresult.txt. That's the results that are shown here, for example. So there it is. So you can get all of the information here. Some of this is not really well developed yet. So for example, the correlations are probably not really reasonable. Well, actually, those might be fine. The errors are probably not reasonable because it doesn't estimate the error yet, and that's something we need to put in. Okay, so and then finally, there's also this fit convergence.dat, which will show you all of the different spectra that. So let me plot that again. Open. I'm going to open it now. This all files, and I will do fit convergence.dat. I don't know why that didn't show up before, but anyway, no, that still didn't like that. Okay, well, if you use a different plotting program, then that shouldn't have problems. But let me check what's in that, just to make sure there's not something wrong with it. Yeah. Okay. So this has all of the data in it for all of the calculations that are done with FEFF. So it starts with, it has it in blocks here. So with GNU plot, it's very easy to plot this separately, but you know, with this plotting scheme, it doesn't really work. So you'd have to use something that you download. Okay. So let's see. We'll go back here. All right, so this is something that you can use definitely for, oh, sorry, I guess I didn't, okay, maybe I'll go back to that. All right, so let's revisit that manganese case, Mn2O3, where we have 2 physically unique manganese sites in the unit cell, 3 physically unique oxygen sites, and potentials should probably be physically different, and we have to sum over a bunch of different sites there. Okay, so you don't have this in your directory, so we'll make it instead. Let's go, I'm going to go to MN203. You can make this directory. You should actually be able to type mkdir MN203 if you want to make a directory in the Corvus _examples. And this has some CIF data here. And actually, I think I can probably share that with everyone. Let me do that. And you can download it. It looks like I can only share from the Google Drive. Okay. Well, in that case, we can always go back to, oops. To here, I think it was, this one was MN304. See if we can find it here. Or did I just use MN304? I don't know. There we go. I think it's this one here. No, that's still MN304. Oops. Let me look and see if I just used a different. Okay. I'm going to open this. I may have done MN304. Yeah, I did MN304. Okay, so let's do that instead, not MN203. All right. So what we really want is something with more than one site anyway. All right, so you can get this from the American Mineralogist and take MN203 or MN304, I mean, Haussmannite, and you can look here, okay, and download that CIF. And I'll post that in the chat so that you can get that CIF. You can always just copy this. Okay. So you can always get that one just directly from there and put that in a fresh directory. And then we can look at my input file, which you can copy as well, which should not be named MN203, apparently. Oops. And you can see what it looks like. I'll copy all this into the chat as well, and you can just make an input file this way. Oops. Accidentally posted this just to DOS, so I will post it again. Okay, here is the CIF file. Or sorry. Okay, here is the input file. And you would get the CIF file here. Okay. So that we can make this input file. And let's look back at it again. Okay, so it's pretty simple. Again, you've got your target list, which is just Zanes, but it has this CF average. So that's configurational averaging. And this, can be used for a variety of different things, but right now it's just going to be used to sum over sites. And then you're going to, instead of setting the absorbing atom, you set the absorbing atom type. And you set it to manganese. Give it a set input, which will be in the same directory here, although you could give this a path. If it were in some other directory, that'd be okay. And then you give it the edge. And I've put these labels down here because by default, if I leave these off, then it will be a pretty big calculation, but probably pretty well converged in terms of the radii here. So I set it to very small radii because it will take a long time to calculate otherwise. So probably you should just keep it like this for now, but if you want to do the full calculation, you can comment those out with the hashtag. Okay, so now we can run this. Run Corvus-I and mn203 or mn304.in. And this will take a little while because it's got to run both of those calculations. But it is running. And here's where the bug comes in, right? This was originally written to just sum over different snapshots of like an MD kind of thing. And so it doesn't have any weightings at the moment. Although I've already fixed it, I just haven't put that in a new release. But this will show you at least the utility of this thing. So it just averages them instead of doing a weighted average at the moment. Okay, so it's done. And we can go back to our JFEF and hopefully try to open this. We'll go back to open again and go into 203. And I'm going to go into this Corvus 2 helper, which does the averaging and the calculations of FEFF, the FEFF calculations. So then I just want to open one of these for now, just so that I can have it in the right directory, and then I can hit plot. And that shows me the first site, the Zane's calculation of the first site. And then I can add the second site if I want. Go back up and Corvus 2, FEFF, and xmu.dat. So you can see these are very different, these two sites. And now if I want to open the average, then I've got this Corvus.zanes_cfaverage.out. And you can see there it's averaged. It's not correct because these should be weighted differently. Again, but this I will be releasing a new version, probably in the next day or two, since I already have this fixed. Okay, so there's also actually one more column in this output, which is nice to have, I think. So if you open it again, for example, this doesn't have a good way to plot this, but if you do column 3 instead of column 2, and I'll put it in green over here, then you can see there's something small here. These are the standard deviations. So if you were doing, for example, configurational averaging with molecular dynamics, then you might want to know the standard deviation of the Zane's curve. And you could plot this with error bars, for example. Okay, so that's one easy thing to do. But let's try one more thing. Because somebody asked a question about this. Let's open up the input file again. And instead of K edges, let's put the L2 edges and the L2 and L3 edges. And if you want, you can do the L1 as well, but I'll just leave it at that for now. And just to note, these will work pretty well. You may have to put, in some cases, more down here in terms of the energy grid to get this just right. But in this case, for L2, 3 of transition metals, it's probably of 3D transition metals, it's probably pretty good with the defaults. So let's go ahead and run this again. And this time it's going to take a little longer because it has to do the L2 and L3 edges for each case. But it should go pretty quickly. So one thing I'll mention while we're waiting for this, especially because we're waiting for this, is that it is pretty easy actually on even Windows, but also on Mac and Linux, of course, to parallelize these calculations. Microsoft has, there's a Microsoft MPI that you can get. It's just, you can just download it for free. Let's just take a look and see. So if you download this and install it, it's going to install in some directory somewhere, and it's not in your path. But if you put it in your path, then you should be able to use it within Corvus and also within JFEF. Alternatively, you can give Corvus or JFEF the entire path to MPI. And then you can make use of all of the cores that are on your machine. So I have 12 cores on this laptop, and many people have at least 6. So, it makes a pretty big difference in terms of calculating things. It's roughly linear scaling. Not quite, but pretty close. Okay, so that's done. And now we can, again, let's just hit plot. And now we see that this is an L-edge calculation. This is just one of the FEFF calculations. Again, this is the L3, I believe. It's the last calculation it did. And we can, again, open, say, the second site. And this will be the last calculation of the second site. Right now, I don't have it saving, or we don't have it saving the files for both L2 and L3. But you can see these are two different sites and they look pretty different, similar to the K-edge. But now let's open the output of the Zane's CF average, which asks for both L2 and L3, and we see it's got both here. So these kinds of things, these, not so computationally intensive, but not so easy to deal with if you aren't used to scripting and coding kinds of situations, are something that should be very easy with Corvus. It at least allows us to use our scripts or to pass our scripts to users that aren't on Linux alone. Because usually in the past we've scripted this kind of thing in Fortran and Bash and various scripting languages, and using Python and the workflow machinery makes it easier for us, but also makes it usable for everybody else since it's so portable. Okay, so let's see. Let me just go back here. That gives us an idea of some of the use that you can, some of the utility of Corvus. There are lots of other useful workflows as well. In terms of fitting, for example, there's more that you can do with the fitting as it is. There are lots of things we need to add, and of course, we're open to, as Tom said before, we're open to all sorts of feature requests. And again, I plan on setting up a forum for this kind of thing. But right now, we can do things like overall expansion of the system, bond length changes, shifts in single or multiple atoms rigidly, which could be important for fitting things like molecules. And then you can fit other quantities like XES, as you can see over here. You can also calculate resonant inelastic X-ray scattering. There is an example for that here, which I'm not going to run because it takes a while, but you can run it at your own time. That's not a huge amount of time, but it takes more time than I want to spend in this. Let's see. There it is, FEFF10, and that's also GeCl4. Favorite molecule. Oh no, this is the molecule that's shown on the screen there, up here. It's this molecule here. So anyway, you're welcome to run that one. And then there also will be soon this full spectrum optical constants. We have this done. It's just not quite in the release version yet. And you can see this. There's work on the archive about this, and it should be coming out soon as well in computational materials science. Basically, this runs FEFF many times to get all of the edges, and then has an approximation that it uses for the optical part of the spectrum. So you can see that it will give you fine structure around all these edges as well. And then once it does all that calculation for the dielectric constant, or the imaginary part of the dielectric constant, it does a KK transform to get the real part. And you can get all sorts of optical properties like the energy loss and the index of refraction and reflectivity and things like that. And then, of course, there are lots of things you can do that aren't just FEFF. As Das mentioned, you can do things with DFT like optimization, ab initio Debye-Waller factors, molecular dynamics plus spectra, and many body satellite effects in XPS and XAS using real-time siesta, for example. All right, so thank you, everyone. And if anybody has questions, please go ahead and ask. And I'll take a look at the chat as well to see if anybody's... yes, the recording will be available at some point on some webpage, probably on the Times webpage. But I can, one thing we can do is we can contact everyone who signed up, who registered for this workshop, and also contact people who have registered for for FEFF10 and tell them where to look for these recordings. All right, so I think that's pretty much it, unless there are any other questions. But otherwise, is there anything anybody wants to see with either FEFF10 or any of the demos that we've done? We have about a few minutes left if we want to do that. All right, so then in that case, again, if you want to contact any of us, you can email me directly or reply to the FEFF10 registration page, or email any of us that we're speaking today about the various codes that came through.
Okay, and I think we should thank Josh for this talk, and thank all the other speakers of this workshop.
Yes, thank you. Thank you, everyone, all the speakers, and all of you who came to the workshop as well.
Hopefully next year we will be in person.
Yeah, that would be nice. Okay, so I think I'll turn off